Hello and welcome. Today, we're diving into the invisible forces that shape, well, just about everything around us, from the weather outside to the very clothes we wear. We are talking about heat and how it moves through our world in some really fascinating ways. Okay, let's kick things off with a simple mystery you've definitely run into in your own kitchen. You put a pan on the stove, right? The metal part gets screaming hot, but the wooden or plastic handle, you can grab it, no problem. So, what's going on there? It seems simple, but the answer unlocks the fundamental rules of how our entire world gets warmed. And hey, we're not the only ones asking these questions. On a chilly evening in Gangtok, a brother and sister, Pima and Paulden, found themselves wondering about the exact same things. Their curiosity is going to be our guide as we investigate the 3 secret ways that heat travels. So, our first clue in this mystery has to do with what happens when things touch each other. This process is called conduction, and it's the very reason that metal pan gets so hot in the first place. You know, this is such a cool way to actually see heat on the move. When you heat one end of this metal rod, the warmth doesn't just teleport to the other side. Instead, as this classic experiment shows, it travels. You can literally watch it happen as the wax melts and the pins drop one by one in a perfect sequence. It's like watching a footprint trail of heat marching down the strip. So here's how it works. Conduction is kind of like a neighborhood chain reaction. One particle gets hot, it starts jiggling like crazy, and it bumps into its neighbor, passing that energy along. The particles themselves don't actually go anywhere. They just pass the heat down the line from the hot end to the cold end. And boom, there's the answer to our first question. Materials like metals are amazing conductors. They pass heat along super efficiently, which is exactly why we make the main part of a cooking pan out of them. But wood and plastic? They're insulators. They're terrible at passing heat, which makes them perfect for handles, keeping our hands safe from the sizzle. Air is actually a fantastic insulator, and we use this trick all the time. Your woolly jumper isn't warm on its own. It works by trapping tiny pockets of air, which stops your body heat from escaping. It's the same reason 2 thin blankets can feel warmer than 1 thick one. It's all about that layer of trapped air in between, acting like your own personal shield against the cold. All right, let's move on to our second clue. While Pema was watching smoke rise from a fire, she noticed something different. The heat wasn't just being passed along from particle to particle, the hot stuff itself was actually moving. This is called convection, and it's all about heat transfer by flow. Just look at this simple setup to see what I mean. When you heat the air under one of those paper cups, that air expands, it becomes less dense, basically it gets lighter, and it physically rises. This upward push is actually strong enough to lift the cup and tilt the whole balance. This proves it. Hot air doesn't stay put, it moves up. And that's the absolute key to convection. It happens in fluids, so we're talking liquids and gases, where the particles can actually move around. The hot, lighter fluid rises, and the cool, denser fluid sinks down to take its place. This creates a circular flow that scientists call a convection current. Now, this isn't just some small-scale effect. This process literally drives our weather. During the day, the land heats up way faster than the sea. So the hot air over the land rises, and the cool air from the sea rushes in to fill that gap, creating a beautiful sea breeze. Then at night, the whole thing reverses. The land cools off faster, so the warmer air over the sea rises, pulling the cooler air from the land out to sea. It's like a giant natural engine powered by convection. Okay, time for our final clue. How do you feel the warmth of a campfire even when you're not touching it, and the air between you might even feel cold? It can't be conduction, and it can't be convection. This third, mysterious process is called radiation. This is exactly what Pima and Peldon were wondering as they sat by their fireplace. I mean, there's no solid object connecting them to the flames, and the hot air is rising up the chimney away from them, and yet they feel warm. How is that possible? Well, the answer is that heat is traveling to them in a completely different way. Okay, so get this. Radiation is heat that travels as energy waves, just like light waves. And because it doesn't need any particles to travel, it can move through the total emptiness of space. This is it. This is how the incredible heat of the sun crosses 93 million miles of pure vacuum to warm our planet. And we use this principle every single day. Light-colored surfaces reflect these heat waves, which is why we wear white and light colors in the summer to stay cool. Dark-colored surfaces, on the other hand, are fantastic at absorbing them. That's why a black car gets so incredibly hot in the sun, and why we tend to wear darker clothes in the winter to soak up every little bit of extra warmth we can get. So now for the big reveal. Conduction, convection, and radiation aren't these separate, competing forces. Out here in the real world, they are constantly working together, orchestrating everything from a simple pot of boiling water to the climate of our entire planet. Just think about boiling water. The burner heats the bottom of the pan through conduction. That heat then gets the water at the bottom moving, creating those convection currents that heat up all the water. And the whole time, you can feel the radiant heat coming off the stove and the hot pan. See? All three processes working together in perfect harmony right there in one single pot. And here's where it gets really big. That same combination of forces you see happening in your kitchen, well, that's also responsible for one of the most important systems on Earth. The water cycle is the perfect example. The sun's radiation heats the oceans. That warm, moist air then rises because of convection. As it gets higher and higher, it cools down and condenses into clouds. And eventually, it comes back to Earth as rain. It's the same three principles: radiation, convection, and the effects of temperature change, just on a global scale, constantly moving water and energy around our planet. So, why does all this matter? Because when we really understand these invisible forces, we can start to control them. And this knowledge isn't just for a textbook. It lets us solve real-world problems in some truly ingenious ways. Look at this incredible innovation from Ladakh. In the winter, they spray water into the freezing cold air, and it freezes into these giant ice cones called stupas. Because of their unique shape, they melt very slowly in the spring sun, releasing water for crops at the exact time when the natural streams are running dry. It's a masterful manipulation of heat transfer. From the simple logic of why a pan has a wooden handle to the complex engineering of an ice stupa, understanding how heat moves empowers us. It lets us build better homes, manage our planet's resources, and even create ice in the middle of a desert. So the question isn't just about what we've already done, but what we'll do next. What other huge challenges can we solve by mastering these invisible forces?